Yeah, so, in case you're just tuning back in, this is the Simon's Quantum Protocols workshop. And our next speaker will be Richard Kueng from Caltech. And he's going to tell us about, getting around this exponential complexity barrier of tomography. Just a reminder, feel free to ask questions in the Q&A window. I'll monitor that, and when the questions pop up, I'll relay that to Richard. All right, Richard, it's all yours.
Hi, everyone. First of all, I want to thank the organizers for making this workshop happen, given the circumstances. I must confess that I was looking forward to this workshop for months now, and I actually tried to adjust my return to Europe in order to just physically make it to the workshop, but now Corona happened, and I'm sitting in Austria, back in my home country, in order to give this talk. And it's also actually a special date because you introduced me as a postdoc at Caltech, but today is literally my last day as a Caltech worker. And tomorrow I'm going to start a new job at the Department of Computer Science at the Johannes Kepler University in Linz, Austria. And I'm very excited to talk to you about a very new and exciting project that we at Caltech did. And I want to give, before I start, I want to give a big shout out to my co-workers, in particular, Robert Kueng. He's an amazing PhD student, and he did all of the numerics I'm going to show you later. And John Preskill is also an amazing co-worker, and his insights and suggestions helped us a lot to kind of do actually interesting numerical demonstrations. So my talk is going to be about exactly overcoming this exponential bottleneck that is associated with quantum state tomography, at least in certain scenarios. So we are going to be interested in finding tractable and efficient techniques on predicting properties like linear or quadratic functions in an unknown quantum state. And the goal we have in mind is to make these ideas, give them a sound theoretical underpinning, but we also really want to branch out to experimentalists. And the main result of this talk will be a NISQ-ready prediction proposal that actually works with, as David calls them, local measurements. So I find this very exciting. And here's a brief outline of my talk. I first want to give a brief motivation and briefly sketch existing approaches to the problem of parameter estimation. And I'm really, really happy that David just gave an excellent talk before me, because he actually took care of a lot of the motivation and existing approaches, namely state tomography. And then I will do something very, very theoretical, because I will assume a very, very general measurement model, and then kind of reason about how we could use such a measurement model to predict a large collection of linear functions. So please bear with me. This might be a bit theoretical, a bit abstract. There will be formulas. But once we have the main theorem, the general theorem ready, I'm looking forward to jumping into concrete examples. And the first example will be computational basis measurements that are kind of preceded by a global Clifford circuit. So I think in David's language, that would be local global, because we do single copy measurements, but we do global pre-processing. And the second example will be local Clifford circuits followed by computational basis measurements. And this is a local measurement procedure. And after we've gathered these results, there will also be some numerics. I briefly want to talk a bit about optimality. It turns out that without imposing additional assumptions, these two example approaches are actually information theoretical optimal. And then once we've properly understood how to predict linear functions, I mean, linear functions are very important in quantum mechanics, but we are also interested in certain polynomials, like subsystem Rayleigh entropies, for instance. And it turns out that our approach naturally generalizes to this regime. And then finally, if I have the time, I want to quickly talk about de-randomization of our protocol. And then there will be a conclusion. So here, very, very broadly speaking, let me zoom out again. I know David talked a lot about that, but the task of my talk will be, we assume that we have an unknown quantum state and we can generate copies. And then we can maybe evolve it a bit, apply a certain gate set or something to like kind of transform it, and then we can do measurements. And the task is to make predictions about this unknown underlying quantum state. And this is a very, very challenging goal, because first of all, there's the curse of dimensionality. If we are interested in n-qubit systems, then a complete classical description of this quantum state is a 2 to the n by 2 to the n matrix. So it's humongous. There's a lot of degrees of freedom. And second of all, I will also assume strong measurements. So once we apply a measurement, we get a classical outcome, but the density matrix is heavily perturbed, and I will actually assume that it ceases to exist. So if I choose to measure, the state is gone. And so in order to overcome this problem, we have to repeat individual measurements many, many times, and then we will have to record outcomes, and these have to be stored in classical memory. And then afterwards, we can maybe use these observed measurement outcomes to compute estimators or predictors for the things we are actually interested in. And for the scope of today's talk, I actually want to treat these different challenges separately. So I want to divide the required resources into the sample complexity, which is how many repetitions of my experiment do I need, adaptive or non-adaptive, in order to have sufficient data. Then I also want to kind of single out the quantum hardware. How complicated are the unitary evolutions or channels I have to apply before I do a simple measurement? And then, of course, we have to store the data, and it better be easy or efficient to store, because otherwise we run out of storage. And finally, I also want to comment and treat classical post-processing, so the actual computation that takes the stored data and transforms it into a prediction of what we're interested in separately. And so the task is to make predictions from quantum measurements. And I also want to kind of work in the local setting where we do single state copy measurements only. And one proposed solution, actually the classical solution to this problem, is to just learn the complete classical description of the underlying quantum state. That's a d by d density matrix. And that's, of course, quantum state tomography. And David talked a lot about this and gave some excellent review about things that happen here. I just quickly want to set the stage, list the 4 different resources we have to consider. And as David pointed out, the sampling rate for quantum state tomography necessarily scales in the big Hilbert space dimension, which might be exponentially large. There's nice information theoretical lower bounds. And if we actually want to predict a large d by d matrix, it shouldn't surprise us that the number of samples has to scale at least kind of linearly in the rank and then linearly in the ambient dimension. And as you note, I actually put a square in the rank here because I'm looking at single copy measurements. John Wright and Ryan O'Donnell, as well as Sean-Woo Ha and others among Aram Harrow, could show that if you had the possibility to do entangled measurements across many copies, you could get a single rank factor here. And then the quantum hardware, that's the redeeming factor of quantum state tomography, at least to some extent, as David pointed out, can sometimes be tractable or rather easy. David talked about local measurements, but the recovery guarantee I have in mind here actually requires Clifford circuits. So Clifford circuits are at least only polynomially big, but they do require entangling gates. So I wouldn't call that technically very, very tractable in current NISQ devices. And then to round it off, classical storage is, well, the size of the density matrix to save. And the classical post-processing time of this projected least squares I actually have in mind here is order dimension to the power of 4. And here I want to stress that this is for general rank R quantum state tomography. And if you're willing to impose additional assumptions on a state, there might be considerable improvements. For example, if you are very confident that the underlying state is well described by a matrix product state with low bond dimension, then you can actually recover such a matrix product state description with substantially fewer measurements, actually polynomially meaning. This is something that David worked on. And more recently, which is more of a heuristics, but it also seems to work very well, deep neural networks. If you train them on measurement outcomes, then they heuristically seem to be able to actually predict a lot of properties of the underlying state reliably. And so it is also possible to view neural network tomography as kind of a specialized approach of quantum state tomography. On the other hand of the spectrum is something that's called shadow tomography, and it dates back to Scott Aronson and Rothblum in this case. And the task here is to like really rethink maybe the general solution of quantum state tomography, because quantum state tomography gives you a complete classical description, which is exponentially expensive. And so it answers all possible questions. But maybe we actually don't have to learn the full classical description, but it is enough to predict certain features. And for the first part of my talk, I actually want to restrict my attention to linear features, and Scott Aronson does precisely that. So Scott Aronson considers the problem of predicting linear functions that I wrote here as trace inner products with some observables, O1 to OM. And you just want to accurately predict a collection of possibly very many linear functions, but you don't have to learn the full density matrix. And then Aronson, and later Aronson and Rothblum, found a beautiful protocol that showed that if you're only interested in predicting m such functions, then a sampling rate that is kind of polylogarithmic in the number of predictions and only polylogarithmic in the ambient big dimension, and there's like some epsilon dependency on the accuracy, only these many copies of rho suffice to actually epsilon accurately predict all of these properties simultaneously. And I find this very exciting because, again, the number of predictions only enters polylogarithmically, and the ambient dimension enters logarithmically. And so if we have n qubits, then 2 to the n square becomes n squared in this case. Like, it's a very, very nice theoretical result, but the underlying procedure is actually non-trivial. And I don't want to go into details, but if you actually want to run this procedure, there's big demands on the quantum hardware. You actually need a quantum memory, and you have to apply exponentially long circuits to tensor products, kind of like you have to store all your copies in memory and then apply exponentially long quantum circuits to this big tensor product. And also the storage is exponentially large, and it's not entirely classical. And the post-processing time is also scales in a big dimension, and it's also not entirely classical. But of course, the sampling rate result, I think, is really, really interesting. And of course, Scott is not the first person to consider the problem of predicting linear target functions. There's like a wealth of existing ideas in the literature. I just want to like quickly point to two such procedures that will be relevant for our talk today. And this is like direct fidelity estimation, a very nice procedure that Flamier and Liu developed. And also Bridges et al. In Innsbruck came up with a nice protocol for predicting many subsystem entanglement entropies at once. We'll see those later.
Richard, I have a quick question.
Yes.
And maybe, I don't know if Scott's on the line, but this exponential complexity for the processing and storage,
yes.
Is this believed to be inherent? Like there are states for which, distributions of states for which this...
I think just like the general procedure, the way it is framed, I hope maybe Scott can chime in,
Hi.
but in general, it has these requirements.
Hi, you want me to address that? I mean,
yes, please.
So the answer is, first of all, if you need to store the state, like a description of the state, that's already, d squared complexity,
yes.
right? If you, need to write down all the answers, that's already m complexity.
Yes.
Now, what you could hope for is that the data would be given to you implicitly, in some like circuit representation, and then your output would also be implicit. And in that case, we have some evidence that there are inherent computational limits. In particular, if you could always do it computationally efficiently, then you could always simulate, you could always replace quantum advice by classical advice. Example, so like BQP / Q poly would equal BQP / poly. Okay, and also like No, I mean, there would be a few other strange consequences, like, I guess, there like for like quantum copy protection, quantum money, things like that. I would love to know better the complexity theory situation.
Okay, great. Thank you so much for chiming in and clarifying this. Excellent. Okay, so again, really, really beautiful protocol, but it seems a bit too demanding to run it on current NISQ device and maybe even near-term devices. And so but the sampling rate is amazing. And so this motivated us to ask the following kind of general question, namely, can we find a tractable and rigorous procedure that kind of achieves something similar to Scott's procedure? Maybe we have to, of course, we will have to make compromises because we want to use weaker tools and kind of be a bit more near term. And so maybe we can't kind of efficiently predict an arbitrary collection of linear functions, but maybe some relevant ones. And so what we want to find is a tractable and rigorous procedure that kind of learns a classical representation of an unknown quantum states from few simple single copy measurements. So kind of the idea is we perform simple single copy measurements, and then we get some measurement data, and we use this measurement data to construct a classical representation. And ideally, we should be able to use this classical representation that can be efficiently stored on our classical computer to predict many linear and maybe even polynomial properties in a way that is similar to what Scott wants to do. But for us, we really want to have a hard divide between an unknown quantum system and the single copy measurements we do. And then we are in the classical world and we just want to do classical computations with the measurement outcomes that we stored. Okay. And now I think after this motivation, I'm ready to talk about the ideas and the approach that we found. And again, please bear with me. I will be very general in the beginning, but to derive a very general result. And then we will make that a lot more concrete by looking at two very relevant examples. Okay, so here is the measurement setup that we envision again. So kind of we assume that there's an underlying unknown quantum state. Let's say it's on n qubits, the wires represent the qubits, and we assume that we can make independent copies of the state. And then we assume that we are able to kind of sample from an ensemble of unitary circuits. So kind of we have an ensemble of unitary circuits that we can efficiently implement in our measurements. And we sample one element of this circuit family at random. We apply it to rho, and then we modify the state. And then afterwards, we perform a single tensor product computational basis measurement. So after this unitary evolution, we measure the first qubit in the Z basis, the second qubit in the Z basis, and so on unto the n qubit in the Z basis. And what we end up with is a bit string of length n. And now our idea is kind of like this observed bit string of length n is somehow correlated with the input state because of Born's rule. And we also have to take into account the unitary transformation in the middle. And so we can just use the bit string that we observed, map it to a computational basis state, a rank 1 state, and then attach the unitary evolution on the left and on the right in order to remember kind of what we did prior to the computational basis measurement. And now what you can see here very generally is we have a quantum state that comes in and we have a quantum state that comes out, with the difference that like this on the right-hand side, we're in classical world. So this features the bit string that we actually measured and a classical description of the unitary. Nevertheless, we can kind of view kind of the map that takes a quantum state, applies a random unitary from our ensemble, then takes a computational basis measurement and looks at the post-measurement state as a nice quantum channel. And in expectation, because there's like randomness involved, first of all, we choose our unitary evolution at random. And second of all, the computational basis measurement outcomes in a single shot are also random. And so let's just look at the expected, kind of like the expected post-measurement state. And then we can just insert the definitions and kind of let us first single out like kind of the classical randomness that we put in, kind of an expectation value over all unitaries in our ensemble. And then here I've just plugged in Bourne's rule. So kind of there's 2 to the n different computational basis states. And the probability of measuring each of them is given by Bourne's rule. And it would really just be B, U, rho, U dagger, cat B, yes. And this actually defines a quantum channel. It's not so difficult to check that. And this quantum channel is actually kind of nice. It's trace preserving, it's completely positive, and it's also self-adjoint. And interestingly, and it shouldn't come as a surprise to the experts among you, this channel, this expected channel is invertible if the ensemble from which we sample is sufficiently expressive to cover all of state space. In other words, if like the collection of all the measurements I could implement in this fashion is tomographically complete. And let's for now assume that this is the case, because if this channel is invertible, well, the inverse might not be a quantum channel. It's typically not positive semi-definite, but we're anyway on our output already in classical world, and maybe we can do it classically. And so in order, kind of like if we perform one of these measurements once, we get kind of like a measurement outcome, and we can associate this post-measurement state with it classically. And then we can in principle just invert this channel on this post-measurement state, because it's all happening on our computer. And once we do that, obviously by construction, this row hat is a random matrix. This should be hats here, sorry, I forgot them. So like kind of the computational basis state we observe is random and the unitary is random, but by construction, this random matrix is the correct underlying density matrix in expectation. And this is actually the starting point of our idea and our approach to predict many linear features at once, because we will just like kind of like this is a classical description. And whenever we want to predict a linear function, we will replace the underlying state, which we don't know, by one of these snapshots or an average of these snapshots, because then we will be correct in expectation. And each of these snapshots might be an independent random matrix, and then we get rapid convergence. And so a classical shadow collects n independent snapshots. So I envision that I run this experiment n many times, and then I will get n different random outcomes. So like for each measurement, I will probably see a different bit string as an outcome, and I will probably sample a different unitary. And so classical shadows just collect n independent snapshots. And again, by construction, these are all independent random matrices, instances of a random matrix that are in expectation are exactly the underlying quantum state. They are, however, not density matrices themselves necessarily, because we've inverted a quantum channel here, and that's typically not completely positive. Okay, and now we can get started, and let's start with something easy. Let's try to predict a single linear property. So similar to like Scott's approach, but he does many. Let's just do one for now. How can we predict one linear function with a classical shadow of size n? And remember, these are these independent snapshots that equal the true underlying density matrix in expectation. So, well, let's just use this, because I could, in principle, take my first classical shadow. It's classical, a classical description of my observable O. Let's ignore computation costs for now and take the trace inner product. And then I will get a number. And by construction of my classical shadow, this number will be the actual true function in expectation. And now with my classical shadow, I don't only have one such random matrix that I can turn into a random number with correct expectation, but I have n of them. And so a natural ansatz is to boost convergence to this desired expectation value by taking the sample means of all my independent snapshots. And we already know that this is correct in expectation, and we can bound the convergence by using Chebyshev's inequality, like one of the most simple ideas that allow you to kind of reason about random variables. And Chebyshev's inequality tells us that the probability of this sample mean estimator deviating by more than epsilon from the true desired target is bounded by the variance of an individual random number in our sum over the desired accuracy squared. And yeah, there shouldn't be a delta here, actually. That's a typo. And now we just have to understand what this variance is. And let me just like quickly write it out. The variance is by definition the expectation of the square of the random variable minus the square of the expectation. And it's like some small trick here, but kind of since we subtract the square of the expectation, we can actually upper bound this by the expectation of a trace squared, but not of the original target function, but of its traceless part. This is kind of a general feature about variances because we subtract expectation values, and so we can restrict ourselves to traceless, the traceless part of the observable here. And now, kind of like we have an expectation of something we already understood, but with a square, and we can insert the definition of a classical shadow. So this looks a bit brutal right now, but I've really just kind of inserted the definition of a classical shadow and did some minor modulations. And so we again have like the expectation value over the unitary ensemble that we pick off. We have a sum over the possible computational basis outcome states. We have kind of a weighing factor that depends on the underlying state. And the important thing here is that we have this inverse measurement channel, but now applied to the traceless observable and then rotated by the unitary and then inner product with the computational basis states squared. And this is actually kind of like a not so nice property because you can see that it explicitly depends on the underlying state. And kind of when I want to get a priori bounds, I never want to like be dependent on the actual underlying state, which I don't know. And so I can find a further upper bound by replacing the state by the maximum over all possible states. This is certainly an upper bound. And what you actually can also check is that this expression on the right for any unitary ensemble defines a squared norm. Because maybe like this is kind of like a weighting factor, a sum of weighting factors. This is just an expectation. And here we have kind of like squared matrix entries on some diagonal. And so this defines a squared norm very, very generally. And this norm depends on the measurement ensemble that we use, but not on the underlying state anymore. And now we actually have a lemma just with Chebyshev's inequality, namely that the shadow norm squared characterizes the necessary classical shadow size, so the necessary number of independent measurement repetitions we need to ensure that we predict our single linear function up to accuracy epsilon with high probability. And the number of samples is really just this shadow norm of the traceless observable over desired accuracy squared or times probability of failure delta. So far, so easy. But now,
what's O sub 0 in the?
Sorry, this should be O bar, and that's again the traceless part.
Okay.
It's just the traceless part of the observable, which kind of makes sense, because suppose that we wanted to predict the trace of a density matrix, then we know that it's 1, and kind of a reasonable, and the traceless part of the identity matrix is 0 because we kind of don't need a single sample to actually reason that the trace of a density matrix is 1. Yeah. Thanks for pointing that out. And now let's kind of switch gears just a little bit. It's not going to get much more complicated to like ask the question about, can we also predict many linear properties? This is really one of the exciting things of Scott's protocol, that he can just predict m different linear target functions with just polylogarithmically many measurements. And so let's try to do that as well. So kind of we want to now not predict a single observable, but m of them, and think m of being a potentially large number, but we want to predict all of them with the same classical shadow, with the same collection of random snapshots from our simple measurement. And then like the naive idea is kind of like, let's just stick to the sample mean estimator that we had before and just apply a union bound. So kind of now for each OI, I just use the sample mean estimator. And here it should actually be a sum over the rows. And then we can actually use a union bound to check how large the probability is that at least one of them, the maximum, deviates by more than epsilon. According to the union bound, I gain a factor of m. This is scary because it's a potentially large number, but I can pull the maximum outside. And now I'm kind of in the single prediction regime again. And if I just kind of insert the insights from Chebyshev's inequality, I kind of get a maximal shadow norm squared here over epsilon squared. And then I get an m over probability over failure probability. But this is actually kind of really bad because it tells me that the number of samples I need in order to predict m properties actually scales linearly in m. And kind of the rest is just very reminiscent of what we had before. But like this linear scaling is like very, very different from what Scott Aronson achieved. And so we probably have to think a bit harder. And there's a better idea actually of kind of solving these kinds of problems. And it's median of means estimation. It's like a very simple, beautiful trick that dates back a long time ago. And I think the brother of Umesh Vazirani, who is an organizer here, was one of the inventors of this. And the idea is very simple again, actually. It's really cute. Instead of like kind of constructing a single collection of random snapshots and using all of them to predict a single sample mean, you kind of do data splitting and create kind of like K batches, capital K batches. So like you take a few more measurements, but then you construct K different classical shadows. So like kind of really, instead of like just using one sample mean, you kind of like construct K different batches, and then you construct K associated sample means for each of the properties that I'm interested in. So here in the first line, we're interested in just predicting the first observable. And so I use the first batch to compute a sample mean associated with my first prediction. And then I use the second batch to construct a linearly independent one, and I go on. And then I use the kth batch to construct yet another sample mean. And then rather than taking the mean of them, I take the median. So kind of I take a median of sample means. And I do the same for all different properties that I'm interested in predicting. So there's m of them. And the trick is not that it's really just this median of means trick is very powerful because now we can go back to our probability bound. Like what is the probability that a maximum deviation is larger, greater or equal than epsilon? I again do a union bound to pull the maximum outside. I have to pay a factor of m, but this time I don't care so much because here I'm again like kind of in a single prediction procedure. And now here is where the median does its magic, because OI is now a median of K different sample means. And we know that the average expectation of each sample mean is OI. And so when does a median of random variables deviate by more than epsilon from its target? Well, in order to do so, at least half of all the sample means have to deviate from their expectation value by more than epsilon, at least half of them. And this becomes exponentially unlikely in the number of sample means that we consider. And so unlike before, you now get actually now an additional, like this looks very similar to what we saw before, but we get an additional exponential suppression in the number of batches K. And this actually does this trick. And it tells us that if we take a total of like maximal shadow norm squared over desired target actually squared for each of our batches, and the total number of batches is logarithmic in the number of predictions we want to make, then we can actually ensure that we get all of them up to actual accuracy epsilon with very high probability. And this now only scales logarithmically in the number of measurements and is actually the main result of our work. So kind of for our general result, remember again that we started with a very simple single copy measurement procedure where we kind of have a measurement primitive, namely that we sample a unitary rotation from an ensemble. And this defines a measurement channel. And we can use this average measurement channel to define our snapshots, which are just like kind of the post-measurement states stored classically and then inverted, and then apply, and then kind of you apply the inverse of the channel to ensure that it has the right expectation value. And then our discussion about statistical convergence also motivated the definition of this shadow norm, which also depends on the measurement primitive. And now with these three very general concepts in mind, here is the main theorem that we have actually just proved. So suppose we're interested in predicting m fixed linear target properties in an unknown state row, then a classical shadow of size, like the number of measurements we need to build this collection of classical shadows, is the total number is number of measurements per batch times the number of batches. And this indeed scales logarithmically in the number of predictions. It scales inverse quadratically in the desired accuracy. And there also features the maximum of all shadow norms. And once we have this larger collection of our classical snapshots, then we can predict all properties via median of means estimation with very high probability. Let me emphasize again that this sample complexity, this number of measurements, depends only logarithmically on the number of predictions we want to make. And it's the shadow norm, not the huge ambient dimension, that determines the cost. So there's no dimension factor here yet. It might pop up with the shadow norm. Okay.
Richard,
are there any questions at this level?
Yeah, could you say some more about this shadow norm? Like, what's the range of it, and how should we think of it?
Maybe can we postpone this? Because in my experience, also for me personally, this thing, the shadow norm, became a lot more graspable when looking at examples.
Okay, sure.
But thank you. Okay. Now, this is a very general result. It's probably too general to like convey much intuition, but I still believe it's kind of powerful. And in order to demonstrate this, let us do like maybe the slickest example that I can think of, that we could think of. And the example we want to consider first are global Clifford circuits. So we again have like the measurement setup that I discussed before. We have an unknown quantum state. And now we assume that we are able to apply arbitrary Clifford circuits to it. And not only arbitrary Clifford circuits, but we actually sample a random Clifford circuit and apply it to the state. And then we perform a computational basis measurement. And then once we do that, we again record a bit string. We remember the Clifford we applied, and we construct or store the post-measurement state U dagger bcat bbra u on our classical computer. And then it's actually possible to like really find very nice closed form expressions of all the rather abstract properties that I discussed before. And it's all thanks to the fact that the Clifford group, at least for n qubits, forms a 3 design. This will allow us to compute these things actually. Now here, let's first look at the measurement channel, which is kind of now an average over the full Clifford group of a sum. And now here you can probably see that U features twice and U dagger features twice. And now the fact that the Clifford groups form as a 2 design allows us to replace this property by an integral over the full unitary group. That's the definition of a 2 design. And you can actually use Schur-Weil duality to compute that. And in the end, what you will find is that the expected measurement channel is really just a depolarizing channel. And the depolarization parameter is 1 over dimension plus 1. And depolarizing channels are like kind of really nice. In particular, it's very easy to invert them. And so kind of the classical shadow is the inverse measurement channel applied to our post-measurement state. And this is really just dimension plus 1 times the post-measurement state we observed minus the identity. And if we ignore the identity matrix for a moment, note that this is actually proportional to a stabilizer state because it's a computational basis state and we apply a Clifford unitary to it. And this is good news for storage. We can actually store these guys efficiently. And finally, let's talk a bit about the shadow norm. In the shadow norm, we again have an average over the Clifford group But now we have an additional square here. And if you were to count, the unitary U appears 3 times, and the unitary U dagger also appears 3 times. And we now also have an inverse depolarizing channel here, which kind of introduces potentially scary dimension factors. But the fact that the Clifford group forms also a 3 design allows us to replace this average with an integral over the harm measure, the full unitary group. And then we can again use Schur-Weil duality to actually compute it. And it's possible to obtain a rather simple upper bound, which is just 3 times the Hilbert-Schmidt norm squared of the observable that we started with. So for the measurement primitive where we apply global Clifford circuits, the measurement channel is a depolarizing channel. The classical shadow is a scaled version of a stabilizer state. And the shadow norm squared is really proportional to the Hilbert-Schmidt norm squared. And here's maybe like just a simple intuition about why this might be the case. And here's a V-bit visualization of a stabilizer measurement. So kind of like in a V-bit, there's only 2 Cliffords, and there's like the computational basis and the plus minus basis. And suppose we have a state that hides somewhere here. Then if we do measure this measurement, like the POVM associated with these 4 measurements, then you note that these guys and these guys will be more likely to occur than the ones that are further away. And so if you kind of like just use that and form an empirical average of like all possible kind of like you just like kind of average the outcomes, then you will at some point get exactly the measurement channel, the average channel in the limit of infinite repetitions. And you can probably see visually here that it's really just a map that takes rho and pulls it inward. And this is exactly what a depolarizing channel does. And this intuition extends to arbitrary powers of 2. Okay, with this, we have a corollary of our main result, which is hopefully a bit more graspable. Suppose we are actually in this regime where we can like apply a random Clifford unitary followed by a computational basis measurement. Then classical shadows, kind of like the inverse, the slightly modified post-measurement states, classical shadows of a total size that is logarithmic in the number of predictions we want to make, scales inverse quadratically in the desired accuracy, and scales proportional to the maximum Hilbert-Schmidt norm squared of the things we want to predict, suffice to predict M linear target properties via median of means. And so the sampling rate is independent of the dimension, but it actually scales with the Hilbert-Schmidt norm. And this can be good or this can be bad. For instance, if you're interested in direct fidelity estimation, like Steve Lamere and Yikael Liu were, then our target is really just a pure state. And the Hilbert-Schmidt norm is 1. And we can deduce that if we are just interested in a single direct fidelity, then a number of samples, a number of measurement repetitions is just inverse proportional to the desired accuracy squared actually suffices. On the other hand, if we're interested in predicting an observable, like X on every qubit, then the total number of measurements has to scale exponentially in a number of qubits because the Hilbert-Schmidt norm of an observable is huge. And locality doesn't help here. On the quantum hardware side, kind of like the procedure only requires Clifford circuits and computational basis measurements. So Clifford circuits only have polynomial depth, but they still require entangling gates. So they might still be a bit challenging to implement in today's devices. But the classical storage is pretty good because we only have to store stabilizer states or slight motivations thereof. And the classical post-processing cost is actually dominated by the cost for computing an overlap between the stabilizer states we stored and the predictions we want to make. So that's also pretty good. And applications, as indicated already, are pure fidelity estimation. And you can also actually use this protocol to predict many entanglement witnesses at once if you want to certify or detect entanglement. Here's a quick numerical experiment that kind of demonstrates that this works. And it should also be like a stylized proof of concepts that these ideas can, at least in theory, scale. And the underlying state, the unknown state, we consider is a noiseless or a noisy GHZ state on n qubits, and we vary n. And the target, it's a bit uncreative, but just consider it as a proof of principle, is the quantum fidelity with a noiseless GHZ state. And in these numerics, we actually compared with neural network quantum state tomography, which recently gained a lot of traction, which is a heuristics approach, by so far still heuristical approach that seems to scale well in number of qubits. And on the left-hand side, we plot on the x-axis the number of qubits in the GHZ state. So we go from 0 to more than 120. And on the y-axis, we denote the number of experiments, the number of measurement repetitions, or the size of the classical shadow that is required to achieve an 0.99 fidelity with the noiseless GHZ state, given that we actually measure a noiseless GHZ state. And what you can see here is kind of like just a support for our theorem. The number of measurements we need to do is completely independent of the ambient dimension, while neural network quantum state tomography scales linearly with the number of qubits. And on the right-hand side, we did a small twist. We actually didn't consider an underlying noiseless GHZ state, but a GHZ state that is subject to a phase flip. And here on the x-axis is the probability of a phase flip. And here on the y-axis, you find the estimated fidelity with a noiseless GHZ state. And you can see the kind of feature prediction with classical shadows really tracks the linear decay in these fidelities. Okay, so far.
Richard, can I ask a question?
Please.
Okay, hey, this is David speaking. So before you go on, so of course now we know that if we don't have random Cliffords, but if you have random Cliffords with a system size independent number of T-gates thrown in, then
yes,
you get unitary T-design, no?
Yes.
Would that help you at all?
Not really. Kind of, we actually worked hard to de-randomize it to get it down to 3 designs using the median of means trick. And so kind of like, if you were to like, kind of like, as an extreme example, if you wanted to like just compute the required number of measurements or data points you need to do median of means prediction with the Haar measure, then the analysis would be completely equivalent to the Clifford case.
And maybe there's hope that maybe the shadow norm could be smaller or something like this?
No, the shadow norm kind of, the way you compute it is you really use the 3 design property and you kind of equate it to the Haar measure, to the Haar average, because it only requires 3 moments. And then you're there already.
All right. Okay. So I guess I should have waited for your optimality chapter then.
Yes. I think what happens, of course, is actually if you were able to do Haar random unitaries, then you could get rid of the median of means trick. You could just take a sample mean and concentration of measure will tell you that this works out fine.
Yeah, that seems like a minor potential advantage.
Okay, but yeah, thanks for the question. But like kind of the shadow norm is completely identical for Haar random unitaries. Okay, so global Clifford measurements are actually kind of conceptually nice, like all the properties that are involved become depolarizing channels or Hilbert-Schmidt norms. So it's actually kind of fun to reason about them. But of course, they have the problem that in order to implement a random Clifford circuits, you have to do entangling gates. And entangling gates are pretty challenging. And so let us go to our second main example, which is local Clifford circuits. So now I again assume that I have an n-qubit system, but instead of like being able to apply a big random Clifford, I only allow local random Clifford unitaries that act on 1 qubit exclusively, followed by a computational basis measurement. And just note that kind of this measurement primitive is actually equivalent to a local measurement technique that David talked about, where you can basically measure in random Pauli basis. Because kind of like the computational basis is just a Z basis, and a random Clifford unitary can rotate it to an X or a Y basis. So kind of like the local Clifford circuit measurement primitive is just Pauli basis measurements. And so we assume that we can do this, and then we record the post measurement state classically. And because everything is local here, our classical snapshots, our post measurement states actually factorize, decompose completely into tensor products, which is a very, very nice property that hopefully already alludes to some of the potential applications of this entire procedure, we will see that it is very well suited for predicting local properties. And so you can actually just use the trick from the global Clifford computations that I mentioned before to also apply it here, but on a local level. So in order to make the computation of the average measurement channel easier, let me assume that I have a tensor product state, like linear extension will allow me to reason about arbitrary states, but this makes it easier. If I apply this average measurement channel to a tensor product state, then everything factorizes completely. I get a big tensor product on the outside, and everything inside is actually a two-dimensional variant of the global random Clifford computation that we already did. And we already know what this expected measurement channel is. It's a depolarizing channel, and the parameter is 1 over dimension plus 1, which is in this case 1/3. And then because we have a big tensor product, we have an n-fold tensor product of that. So kind of also the measurement channel acts locally. It's just local depolarizing channels on each of the qubits. And now the depolarize, kind of like the classical shadow, our snapshot that we want to store is the post-measurement state that we observe, and then we apply the inverse channel. But because this factorizes into tensor products and this factorizes into tensor products, the entire classical snapshot is just itself kind of not a tensor product state because it's not positive semi-definite, but it's a tensor product of very, very simple objects. And note that if I were to trace out kind of like each local constituent here has unit trace. So I can actually like trace out parts of this classical shadow that I'm not interested in. And last but not least, I'm not going to do it here, but you can also find relatively tight bounds on the shadow norm. And it turns out that the shadow norm scales exponentially in the locality of the target function I'm interested in. So if my target only acts non-trivially, let's say on 10 qubits, it doesn't matter where they are, then the shadow norm can be upper bounded by 4 to the 10 times the operator norm squared of this property, and operator norms of observables are typically bounded by 1. And here, locality of O really just measures the number of qubits on which O acts non-trivially. And so this is kind of like very, very different from the global Clifford measurement primitive that we saw. And by like just invoking the main theorem I showed before, we can conclude the classical shadows of this total size based on a local Clifford measurement primitives, like really independent random Pauli measurements, suffice to predict M linear target properties via median of means with high probability. And again, now kind of like it's logarithmic in the number of predictions, and the number of samples now scales exponentially in the locality, but is again independent of the ambient dimension. And so if we're interested in predicting local observables, then this is good news, because the number of samples we need really only scales exponentially in the locality. But if we're interested in non-local observables, then the total number of samples we need with this procedure is actually exponentially large. Now, the quantum hardware here, I think it's really kind of reapproaching the NISQ regime, because it's really just being able to measure random Pauli bases for each new data point. The classical storage is also very benign. Like we only have to store product states essentially that are also stabilizer states. And if we're interested in classical post-processing, we have to compute overlaps between these states and the observables. And this is dominated by the largest locality, because we can just trace out the part that we don't care about. And possible applications are kind of more physical properties like K-point correlators, or like energy of local Hamiltonians, or like Hamiltonians that are comprised of sums of local observables. And let me quickly show some numerics here. So here we again compare our ideas, mainly linear feature prediction with classical shadows and random Pauli measurements or local Clifford measurements with neural network quantum state tomography, which gained a lot of traction. And here we assume, in this first numerics, we assume that the underlying state is the ground state of a 1D critical antiferromagnetic transverse field Ising model. These models are interesting because they have only a polynomial decay of correlations. And we want to show that. And so the target is like, now we want to predict many features, namely all 2-point functions that connect the first site with all the other sites in a lattice of size 50. And here you can see kind of the results. The blue line is the true value, the value analytically obtained by doing DMRG or MPS approximations. And you can see the classical shadows and neural network tomography kind of nicely track that. And both use the same number of random poly measurements. So kind of this is a fair comparison. And you can see they are roughly comparable. Now, as a second numerics, we can go to 2-dimensional lattice models. So we consider the 2-dimensional antiferromagnetic Heisenberg, the ground state of that Heisenberg model on an 8x8 lattice. Kind of DMRG becomes challenging if you go to 2D system. And the target is, again, all 2-point functions in this Heisenberg model. And we again compare with neural network quantum state tomography. And here you can see kind of what this correlation table, it's now 2-dimensional because we can go in 2 directions, should look like according to DMRG, which we consider to be analytically. And here you can see what neural network quantum state tomography delivers. And here you see feature prediction with classical shadows and median of means. And you can see they're all pretty similar. It's actually difficult to spot differences, but there's maybe a few more hallucinations down here. But again, the methods are comparable. Where they really start to become different is if we do a runtime comparison. So kind of neural network quantum state tomography is based on like doing these measurements and using these measurements to train a deep neural network. And this deep neural network is then used as a classical representation of the underlying quantum state. And typically training neural networks is not cheap. Whereas kind of the prediction procedure that we propose is really just remember the measurements outcomes you had, like do minor modifications thereof, and then take sample averages and maybe medians of sample averages. So everything is, apart from the median, everything is linear there. And you can actually see this in this plot that the runtime between classical shadow prediction and neural network state tomography is rather extreme. Namely, you can see here for the numerical experiments that I showed earlier, there's roughly a 10⁴ difference in classical post-processing time seconds, which shouldn't come as a surprise. But the results both methods give are rather comparable. Okay. Now, let me very, very briefly talk about optimality. Actually, we have seen 2 concrete examples for linear prediction with classical shadows. So kind of just store the measurement outcome. You use it to form the post-measurement states on your classical computer, and then you invert the measurement channel to get something that is correct in expectation. And we saw that kind of if we have a global Clifford measurement primitive, so we are able to do random global Cliffords in the middle, then the number of samples we need to predict M-linear features scales with the largest Hilbert-Schmidt norm of these features. And then we also saw local Clifford measurements, and there the number of samples required to predict linear function scales exponentially in the locality. And while these things might make sense, it's a natural question to ask, are these sampling rates necessary? And in order to answer this question, I quickly want to point out that linear prediction with classical shadows has 2 core properties, given that it's a very, very naive or simple procedure. First of all, let me reinstall, we assume single copy measurements. So copies of the quantum state are measured independently. And then the second feature is maybe a bit more crucial, and it's not necessarily, I think, maybe a bit too naive, but the data acquisition is also oblivious and ignorant with respect to the predictions you actually want to make. So kind of if we assume the local Clifford measurement setup, then like kind of the data acquisition phase is really just choose a random poly basis, measure it once, get the bit string, remember the poly matrix, and then repeat. This is completely independent of the actual predictions we want to make. And it's also non-adaptive. And you can actually show that any linear prediction technique that is based on oblivious, so kind of oblivious, it's a universal independent measurement data acquisition phases that are also based on single copy measurements kind of require an order of state copies to achieve the prediction task that is exactly comparable with the upper bounds we got for our feature prediction with global Clifford measurements. And if you actually also instantiate that you want to do local measurements, so kind of only single qubit rotations that are also oblivious and only act on single copies, then you can show that the number of state copies that is required to accurately predict a worst case collection of M observables also scales exponentially in the locality and quadratically in the operator norm. But note that here the lower bound is a 3 to the locality, whereas our upper bound is only a 4 to the locality. So there's a small gap. And I don't want to say too much about the proof idea. It's actually pretty standard. We are inspired by relating feature prediction of M different observables to a task in quantum communication complexity. So suppose that such a device existed that can predict M features very, very accurately, then you could use that to transfer information by encoding. Alice could, for example, encode classical information into N qubits, send it to Bob, and Bob could then use this hypothetical device to kind of decode Alice's message. And yes, and kind of these ideas go back to David Gross and Steve Lamia in 2012, and then they were later refined by John Wuhan and Aram Harrow and others to find tight lower bounds for quantum state tomography. And the one twist we do here is that actually we allow for kind of a semi-mischievous agent that kind of randomly rotates each quantum system. Kind of he intercepts it, he rotates it, and then he forwards it to Bob, and he stays quiet. But kind of after the data acquisition phase on Bob's side is completed, the mischievous agent actually reveals his unitary to Bob. And this kind of pinpoints the difference between an oblivious prediction technique and a general tomographic prediction technique, because an oblivious technique can handle such a semi-mischievous agent, because even if the data is already collected, if the data acquisition doesn't depend on the things you want to predict, you can kind of rotate your codebook classically afterwards and still decode the relevant information. And by doing this, kind of like, yes, if you can commit M bit, then the mutual information has to be log M, and then it has to pass through here, and then you can simplify. And in the end, what you will see is that the lower bounds pop up.
Richard, just a quick time warning.
Yes. How much time do I have left?
Minus a couple minutes.
Oh, minus a couple of minutes. Sorry, I don't have a time here. So maybe very quickly, you can extend these ideas to predict polynomial functions as well. Kind of the entire idea generalizes, and you have to use U statistics. And with this, you can predict Rayleigh entanglement entropies of subsystems. And this works very, very well. It's also very efficient. And yeah, with that, I actually want to conclude and thank you for your attention. I'm sorry for going over time.
All right, thanks, Richard. So, please feel free to type in your questions. And while maybe people are thinking about their questions, I guess I didn't fully understand. So it sounds like the scheme you proposed, actually the measurements that are performed are independent of the predictions that you want to make.
Yes.
So somehow that seems, can you say a little bit more about how, like, why the number of, there's a dependence on the number of measurements then? Because, you make this shadow, but it should work in principle for any measurement you walk up with, provided that the shadow norm is small.
Mm-hmm.
But it doesn't know in advance what measurements you're going to ask about.
Yes, but kind of like, yes, that's true. But kind of a necessary condition is like kind of you can first do the data acquisition, but our constructive theoretical convergence guarantees only hold if the number of measurements you actually did is proportional, for instance, to the largest locality squared. is it just like kind of like for any collection of M observables, this number suffices to ensure that you can predict all of them accurately with high probability, but the precise nature of these observables doesn't play a role.
So if you, let's say, you know, you picked a sample size like n, and then you ended up trying to predict more than the requisite number of
yes,
allowed number of measurements, would it like suddenly fail after a point, or like
no, I actually don't think so. It's just like kind of like the constructive results fail to hold at some point, and also like if the number of measurements or the number of questions you ask becomes too large, the entire argument breaks down. Because you could in principle like look at the classical snapshots that I have and kind of like at the linear prediction technique that I use and kind of like try to find directions in state space where like my data is very, very bad, and then you could start breaking it.
So there's a couple of questions in the Q&A, but before I turn to them, I think maybe now's a good time to maybe allow people to take a break. So let's reconvene in 10 minutes, say. So, that would be 12:50. So, yeah, so you know, let's meet again at 12:50 Pacific. And in the meantime, let me turn to the Q&A questions. So people are asking about the de-randomization strategy. So if you'd say a few words about that.
Okay, yeah, of course. Kind of on a high level, what this entire like de-randomization for local Clifford measurements. So this addresses the Niski case of like classical shadows from local Clifford measurements, where you really do like kind of random poly measurements. And then you record the measurement outcome that you observed and the unitary, like kind of the basis, the poly basis that you measured in. And kind of what our result says is forget for now the things you want to predict. Kind of like just measure random poly strings. And if you measure sufficiently many of them, then with very high probability, you will be able to predict many local properties at once. Okay, this is kind of like what our main result says, and this can actually be viewed, it's a probabilistic result. So with high probability over all possible poly basis measurement collections I could do at each step, with high probability, I will get a measurement collection that allows me to predict all of these local properties simultaneously. And kind of this, from a probabilistic point of view, this can be viewed as an existence proof. So because if I randomly sample all my measurements and I succeed with high probability, it means that there's like a deterministic strategy that allows me to do that. And suppose now, let's switch gears. Suppose that we know the targets that we actually want to compute, then you can actually use the method of pessimistic estimators to de-randomize the measurement procedure completely. And the idea behind that is kind of like again, let's assume we are doing the first measurement, kind of like the first random measurement. So if we kind of like in our original protocol, we sample the first poly at random, poly basis at random, second at random, third at random, and our probabilistic guarantees tell that with high probability, a random collection will yield accurate results. But now I have three choices for my first measurement, X, Y, or Z. And our theoretical results tell me that on average, over all three choices, I will do well. And now this in particular tells me that there is a particular choice, either X or Y or Z, that kind of achieves, or like kind of that achieves, that also performs well, or maybe even performs better than a random choice. Does this intuitively make sense? So there's kind of three choices for my first measurement basis. And our result tells us if we do it randomly, we will succeed with high probability. And now we can start looking at conditional expectation values. Like what is the probability of accurately predicting all targets given that I chose X, the X basis? What is the probability, what is the conditional expectation of, or conditional probability of succeeding accurately predicting all properties given that I chose Y and Z? And then ideally, one of these conditional probabilities will be higher than the others. And the method of pessimistic estimators allow for making this precise and turning it into an algorithm. So kind of at each local step where you have to make a choice, X, Y, or Z, you kind of take into account what you already did and assume that everything from now on will be done randomly. What is the best choice I can do now? And this turns out to be like kind of linear in the number of qubits, and you can compute it, and you end up with a deterministic measurement procedure that performs at least as well as the random guarantees that we derived, but in practice it performs much better. It kind of gives you an additional 10 times improvement in sample complexity empirically.
So we have another question from Juan, who can.
Hi, so I guess you didn't have time to talk about this nonlinear or polynomial
Yes.
quantities. So do you have an estimate for the, say, Renyi entropies or purity, like in terms of the number of measurements and so on?
Yes, absolutely. Kind of, we did that. If you want to do polynomial functions, let's do quadratic functions, like entanglement Renyi 2 entropies, then the entire intuition generalizes. And the idea is really just that I can rewrite a quadratic function as a linear function in the tensor product. And I take 2 independent snapshots and then average over all possible pairs of different snapshots. And then I will get something that is correct in expectation. And you can again compute the variance, and kind of the number of measurements you need is again logarithmic in the number of predictions. It's kind of exponential in the single party locality of the quadratic functions you're interested. And there's an additional factor of 2 because you're interested in a quadratic polynomial. If you're interested in higher order Renyi entropies, you won't get an additional multiplicative factor of 2, but of R. Thank you.
Hi, Richard. This is Steve Lamia. How are you?
Hi.
Hi. I have a question about if we could just return briefly to the de-randomization.
Yes.
So this pessimistic estimators method, which is fantastic, by the way, this is a greedy strategy, if I understand it correctly.
Yes.
And maybe you said this already and I missed it. Do you have matching lower bounds?
No, we don't, because actually, I seem to remember that with the pessimistic estimator, your rigorous guarantees don't improve. Kind of like the statement is always like, it's kind of like you start with a probabilistic method proof for existence. Like kind of suppose the probability of choosing some collection of measurements such that I predict all of them correctly is strictly smaller than, is strictly greater than 0, then the method of pessimistic estimators will find it.
But is there maybe an information theoretic argument that you could make that would say that this kind of scaling is optimal?
We kind of have information theoretic lower. Okay, now it's adaptive. Yes, I see where you're going. I actually don't know. I just think that the improvement you can typically expect is like kind of constant, but that's a very good point.
I believe you, but I don't know the answer either.
Okay, so let's thank Richard again. That was a great talk. And we'll reconvene in a couple minutes with our next speaker, Adam Boland.